So I'm going to talk about advection again, but in a different context. I'm going to put it in the context of an optimization problem. And this is work done with Pavel Bochev and Dennis Ridzal, also from Sandia Labs. And I'll hope to get you to your coffee on time. So let's get going. So briefly, I'm going to go through the transport problem, which we've already seen quite a bit this morning. Then I'm going to discuss an optimization-based remap that we're using for this. Talk about some details of the implementation and how we're using it on the sphere, and then show some computational examples. So for my talk this morning, I'm going to focus on the scalar transport equation given here. Just for convenience, I'm going to talk about density and mass, but of course this could be applied generally to other fields for a transport. So what we want to do is partition our region omega that we're interested in into cells, and I'm going to be discussing cell mass, the integral of density over the cell, a cell volume, and a cell mean density. Those are the pieces we're interested in. And if you consider the cell to be a Lagrangian volume, you can write conservation of mass in the final equation. And that leads to the formulation that we're using for transport, which is an incremental remap type of formulation. And many of you, of course, are familiar with this, but I'm just going to go through how it works briefly to get everybody on the same page. So we start, let's see, there we go. Okay, we start with an original grid. And if you consider a cell in the center here with a given cell average density, we advect the cell in time. And so here we have that same cell at t plus delta t. And we want to get new variables for that cell after the Lagrangian transport. And that's quite simple. The mass is conserved, so the mass in the cell is the same. The density is only changed by the change in area of the cell. So that's a simple Lagrangian piece of it. And then what we need to do is remap the density, the cell average density and mass from the old Lagrangian cell into the new, or the original cell we started with. And so what I'm going to be focusing on for the rest of the talk is the remap problem. We're remapping from the Lagrangian cell, which I'll refer to as the old cell, to the original cell or the new cell. And all the new cell quantities will contain, will have a tilde over them to distinguish. Oops. So now I'm going to define the mass density remap problem. So we're given a mean density in an old set of grid cells and a mean and a mass for that cell. And we want to find accurate approximations to the masses on the new cells. And we want to do that keeping some things, keeping some properties that we need. So we want total mass to be conserved first, and then we want the mean density approximation in the new cells to satisfy some local bounds. And this is your monotonicity constraint. And if the density is a global linear function, then we want the remap masses to be exact. So we're going to use we want our method to be linear. Oops. All right, I remember to do this. So how do we formulate this as an optimization problem? So we need three pieces for the optimization problem. First, we need an objective. That is, we want to minimize the distance between a solution, this u hat, and a suitable target u tilde. The variable u here is going to be some function of density, which I'll be describing in later slides. We also need a target. So the target here is going to be a stable and accurate solution to the equation, but it doesn't have to satisfy all the required physical properties. So for example, it could be a high-order solution that isn't monotonic. And then we have constraints. So all the desired physical properties then go into the constraints, and they define a feasible set for our final solution. And the advantage of this is that we can show that the solution is globally optimal with respect to the target and desired physical properties. In fact, for the formulation I will discuss, we can actually prove that there is a unique minimizer. and then you can get it for this. It decouples accuracy in the target from the enforcement of physical properties, which can be nice. And it can allow you to try new interesting feature preserving methods and apply them to arbitrary grids. So the way we're going to implement this optimization is a formulation we call the mass variable mass target. So if you consider an exact mass update, the exact mass in the new cell, M tilde, is actually equal to the exact density integrated over that new cell, C tilde. But if we add and subtract the mass on the old cell, we get an equation like this, where you have the exact mass is equal to the mass on the original cell plus some mass difference. And so we can approximate this mass update operator, where u here as a function of rho is an approximate update to that mass. For our target, then, we define it as this difference in integrals, where now rho h is a discretization of the density. So we're going to use a linear reconstruction for our density to formulate this. So putting it all together, here's a formulation of our optimization problem. We're going to minimize this objective subject to the sum of all ui hats equal to 0, and that's your mass conservation constraint, and these inequality constraints, which are the bound constraints. So that's going to give you monotonicity. And in optimization speak, this is a singly linearly constrained quadratic program with simple bounds. And why is that important? It's important because it means that this problem is really straightforward to solve. It's a global optimization problem, but you can solve it very straightforwardly. So if we don't include this mass conservation constraint, the problem is fully separable. That means you can solve it very efficiently locally. To put this in context, the original formulation that was put forth was a flux formulation. So we were doing it based on the fluxes, which seemed the more natural way to go at first. And if we use fluxes, mass conservation, we get mass conservation for free. But the problem with that formulation is that it becomes a global inequality constraint problem, and it's very difficult to solve. So just changing our focus makes it a relatively straightforward problem. So our solution approach is to solve the related separable problem first without the mass conservation constraint, and then have an outer iteration that solves the mass conservation. So here's a Lagrangian functional that's being used. So again, here is the optimization objective. We have the mass conservation constraint. Lambda is a Lagrange multiplier. And then we have our inequality constraints with Lagrange multipliers, mu. And equivalently, we have, you can think of it in KKT conditions. So what we do is we focus on the separable part first, and we can actually get a solution as a function of lambda, the Lagrange multiplier for the mass conservation constraint. And then we adjust lambda in an outer iteration to satisfy that. And because of the structure of the problem, we're using a secant method that's very efficient, and we always have shown that it's been less than about 5 outer iterations for all the examples that we've looked at. And we do get exact mass conservation to machine precision with this. So now, stepping away from the optimization problem, I'm going to look a little bit more about how we do the remapping, some of the details. So in terms of defining the target, we're using a mean preserving density reconstruction right here. So rho I is the cell average density. This G is an approximation to the gradient, and B are the cell barycenters. The target mass increment is found from the difference of these integrals, but we actually do sum up the fluxes to get this mass increment for each cell. So if we consider a grouping of cells, This is kind of a messy plot, but so the kappa are the cell numbers, and you can ignore everything on the edges right here, but consider a cell kappa 5 here. And we want to remap to this kappa tilde 5 that's more lightly shaded here. If you think about the movement of the nodes, it moves out an area, and this is, I know a number of you also use this approach. It's a swept area from the Lagrangian motion. And so these sigmas are the swept areas between these cells. And so we integrate over the swept areas using Green's theorem to get the fluxes and then sum them up for to get the target mass increment. Just a little bit more about the swept region approximation. So for each of the swept areas, we're only using one density reconstruction. And this describes a little bit how we choose which density reconstruction we use for which swept area. So the density reconstruction depends on mu star, which is a signed area defined on how we go around that swept area. And D is a cell-to-side incidence matrix. But all those are really details of the implementation. It's easier to see graphically how we do this. So if this is kappa 5 or cell 5, for this swept area we use a reconstruction in this cell, and as well for the swept area here. Now for this swept area we use the above cell, kappa 8, and this we use kappa 6. And so we don't worry about any exact intersections for this method. And even using this approximation, we can still prove that it's still linear. We can get a linear function, reproduce a linear function exactly. And it's much more efficient to use swept areas. So one also thing we've been looking at is an adaptable target. The target is not necessarily, and in fact most often, is not going to be in the constrained space where we're looking for our solution. But we can nudge the target, and that will nudge the solution that we finally get. And so one way we could do that is shown here. So we start with our mean preserving density reconstruction that I showed before, and we can define a reconstruction residual. And this residual measures the difference between the solution and a global linear function. And when it's very different from that, we can adjust our linear approximation. So if it's linear, then Ri is 0, and we don't change the density reconstruction, and then we still maintain linearity. The solution is exact for linear still. But if it's not, then we have this alpha that we can modify, and we can steepen things in the case of discontinuous or discontinuities in the density, or seeming discontinuities in the density. And this tends to perform better than slope-limited reconstructions for problems that combine both sharp and smooth features. So finally, everything I've talked about so far has been in Cartesian coordinates. What are we doing for spherical coordinates? As a start, we've implemented it in lat-long coordinates. And in that case, our mean preserving density reconstruction looks like this, where the gi theta, gi lambda now are approximations to gradients that look like this. And then we have b lambda and b theta, which are analogous to cell barycenters for this formulation. And we also integrate over the swept area sigma using Green's theorem, but we have different integrals now that coincide with the lat-long coordinates. So I'm going to talk about a couple examples. In both of them, we're starting from the same initial data, and that's these notch cylinders. We're using a deformational flow field, and I think we've seen these a few times, both today and a little bit yesterday. And then we're using a zonal flow, so just a simple transport. So here are results for the deformation case. We're comparing against a flux-corrected remap method. And then here's our MVMT with the adaptable target. the transport results are at a final time t equals 5 after 2,400 time steps, and we're using a 3/4 degree mesh. So we have some more information here. The top plots are at the point of maximum deformation for this flow, and then the final solution again. And it's interesting, with the adaptable target, the right cylinder seems to come out, come out better with the MVMT formulation. So we're still looking into exactly how the adaptable target is working in this case. But what I want to focus on a little bit is that in terms of errors, our algorithm is analogous to FCR in this case. And don't be alarmed at these times. Right now it's all implemented in MATLAB, and these are run on a colleague's Linux machine. But the point we want to make is that even though we're doing a global optimization problem here, that the timings are very similar for the two methods. Previously, in the flex method, the timings were much worse, and it didn't seem to be a viable option. But now this really is looking like it could be a reasonable solution to an advection problem. And then the final is the rotation case, again on a 3/4 degree mesh. And here you see somewhat of a dramatic improvement between the FCR and the MVMT with an adaptable target. So I'll just skip to the conclusions here. We think that optimization-based transport offers a robust and accurate alternative to conventional transport algorithms with limiters and other things. It seems to work as well as flux-corrected remap. It's easily parallelizable. For Cartesian grids, actually proved that the region where we're finding the target is actually larger for the optimization-based algorithm than FCR. So we can prove that we're looking at a larger feasible set. And separating accuracy from feature preservation allows a lot of interesting innovations, perhaps, in how we do this. And so there are more details in the papers I've listed below.
Yeah, thanks to this talk. Questions?
Is this method limited to CFL less than 1, or to the fact that the deformation should not include points beyond the neighboring cells?
Right. It has to stay within the neighboring cells.
Do you conserve mass locally as well as globally, or?
Well, we're really interested in conserving mass globally. I'm not sure, when you're thinking about remapping from the cell, it's more important to think about the global mass conservation. The Lagrangian step does conserve mass, but the mass even locally in a cell, but then the remap, I'm not sure about that.
Do you have consistency between tracer transport and mass transport?
So that's one thing that we're starting to look at. We haven't looked at systems with this, but that's what we want to look at next.
Could you extend it to 3 dimensions, do you think?
Oh, yes. I think so.
Are there any special applications where you have this in mind, or is it general?
Pretty general. The original method we were looking at doing remapping for arbitrary Lagrangian Eulerian codes. But then it seemed like transport was an interesting application, so that's why we're looking more at transport now.
Did you choose any other norm different from this L2 norm in your objective function?
No, I think the L2 norm gives you nice properties, and you can prove that there is a unique minimizer. Yeah, I'm not the optimization specialist, so there may be other issues, but I think it's because you can prove that there's a unique minimizer.
Just to get a simpler KTT system?
Yeah, I don't think we've looked at other.
Okay.
Yeah. Can this method apply to multi-tracer context? That means you have hundreds of traces to be transported.
Right.
Every time you have to optimize.
So we're thinking through that problem right now. And I'm not sure how we can make it as efficient as some of the other methods that are there for multi-tracer transport. But that's something that we're trying to think about right now.
Okay.
Okay, thanks to all the speakers.